Good morning. My name is Johannes Pernpeintner. I'm from a German Aerospace Center, and we're investigating finding leakages in building envelopes. I guess in this room I don't have to explain that air tightness is an important part of energy requirements of buildings. The measurement of total leakage, I would say, is a solved problem, as we have the blower door or the pulse method. Finding the actual locations of the leaks is still relatively cumbersome, using smoke sticks, infrared cameras, and usually the knowledge of an expert is required there. So our goal is to develop new methods, finding the leakages quicker, faster, easier, and maybe also accessible to more automation, maybe with drones or cars going around or something. And the methods we try to develop further there are using acoustic cameras and active thermography. So if you look at acoustic cameras, this would be the setup. We have a microphone array at the outside of the building and sound source at the inside of a building. You could also switch it around, but this way you could image a bigger part of the facade at once. State of the art, there are ultrasound cameras already used to find leakages in pipes, and using ultrasound loudspeaker and single microphone is also already a product you can buy. In our research, we focus on using sound cameras at acoustic frequencies, so you can really hear the sound usually. And also we try to improve the usage of ultrasonic frequencies by developing a new speaker there. So this is how a setup looks like. At the inside there is this speaker. In this case it's two speakers for two frequency bands. And the idea is to have a homogeneous sound source that radiates in all the directions at once. Currently we're using white noise signal, so I always think about we should use some music or something like that, which would be much more nice for the people during the measurement. White noise, loud, is not very nice to use. We currently use a acoustic camera made by GFIE, a German company from Berlin. It has 48 microphones. Inside there's also a video camera, so it can create an overlay of the sound result to the real world picture. Here are some results. So as we are using quite large frequency bands, we have to switch through manually, in this case, terz bands. So we divide octaves into 3 terz bands. And in this case, we have found, you see the measurement distance was about 8 meters. And we found a signal in the upper right corner here. And then we verified there were cracks in the plaster inside and outside. Here's another result where we found something, again, at the same frequency. But this shows that the method essentially works, but there is still some manual input where we really have to switch through the frequencies and use our pre-knowledge of what could be a leakage there and what couldn't. So here's another example of a result. On the left picture, we found something at the window, and when we looked closer, there was a hole in the window frame. But also we see quite a lot artifacts like vibrating windows or reflections of sound. So this is one of the topics of investigation that we have to, we know that the method works, but in the big data set, we really have to find more automatic ways to differentiate artifacts from real signals. Active thermography is also a known technique for finding leaks. There is the software from blower door, bow tools. I guess usually people just go with the infrared camera through the building, and with activated blower, you look from the inside and see the cold spots. And there our idea is to use advanced algorithms to enable measurements from the outside so that we can also investigate larger surfaces more quickly and more easily. And also improve usability. On the image you also see we want to measure from the outside. So in that case we have to deal with changing conditions in the environment, like suddenly shadows appearing, wind, changing temperatures, cars passing by, things like that. And that is the goal, to have a robust algorithm that can deal with these issues. Here's some example images from a measurement campaign. We have the infrared camera from the outside. In that case, we introduced artificial leaks with some cable binders. And from the inside, there is the blower. And we activate the blower in a usual measurement sequence 3 times with 20 seconds on, 20 seconds off. So the measurement time would be 120 seconds. This is a normal infrared image after 30 seconds. So it would be the first period of measurement. So after 20 seconds, blower on. As you know, you see a lot of things in the infrared image. You might suspect that something is in the upper left corner. We knew from previous measurements that the cable binder on the left side of the door pried open the frame, so we really have a leakage on the upper left side. But you see a lot of other images like reflections in the lens, and also in the foreground there is simply the ground. So the sun was shining directly on the ground. So you see a lot of things. An expert might see something, but it's not straightforward to interpret these images. Classic active thermography, by using Fourier transform, you can create an amplitude image and a phase image. Typically in active thermography, you use the phase image when you investigate electronics or things like that. In our case, we saw that the amplitude image is much more interesting. But also you see a lot of other artifacts, like when the sun was changing during that day, so the wind was very gusty, and also the clouds were moving in front of the sun, so we had a lot of difficulties with stable environmental conditions. So the question then was, how could we suppress these artifacts? And one of the ideas was to use phase filters, so combine the 2 images. And on the upper left, you see again the amplitude image, and then we switch through the phases. And at about 60 degrees, you see the best contrast, where you really amplify the signal from the leakages and suppress all the other artifacts. In order to further investigate these methods, we built a test bench in Cologne. We have access from both sides, so we can put speakers inside, we can pressurize the test bench, we can heat the test bench, and in front we can put several different specimens. Regarding the annex, we see our contributions in subtask 4, objective 4, performance diagnostics, development of new methods. One difficulty will be to use this as a to have quantifiable results. So we see ourselves more of in the field of finding the leaks, but to really have quantitative results will be very challenging there. Thank you.